explain one idea for solution, and then I will ask if someone else has a different idea, different solution, different approach, and then you can comment on your own solution if it's different. And I will go through problems in order of difficulty, where difficulty means more or less how many teams solved it yesterday. Okay? So this is the most interesting for last, where we are more mapped than everything. So the easiest three problems, I'm going to more or less glide through them because every team solved them, and I know there's pretty little point on spending time analyzing. So, for instance, falling guns was probably the easiest one of all. It was just some formula evaluating, checking which one was the highest, and then outputting some other formula. And all the formulas were given in the statement, so there was really almost nothing to think about. Just carefully read the statement because it was long, and figuring out that it was not really difficult. So is there any comment about this problem? So then the pattern locker problem was also somehow easy. I mean, you just have to count the number of combinations of some small number of digits, so up to 10,000 digits. And you need length between, and you have to calculate this number between some given range of lengths, right? So for a fixed length, so if we have L equal 10,000 possible digits, and we want, let's call it K equal to 500, then we know the number of possibilities for this length and this number of choices as digits is 10,000 factorial over 10,000 minus 500. Okay? This is easy because there's no repetition. Okay, and this works in general, right? From this L factorial over L minus K factorial is basically the result for a given length. Now, if we have to sum up multiple lengths, we have to sum up this amount from K equal to from M to N. But since there are several test cases, if we do this by hand, it can take a long time, right? And we are doing everything modulo some big number, so there's really no problem about overflow or anything. But what we can do here is, notice that this is so the last one, the K equal N, sorry, the first one is the biggest one, right? Because each time we divide by a larger factorial. Okay, so what we can do is we can group all together, taking common factor, and then all we have to do to calculate this, the part that gets inside the summation quickly is to accumulate the sum of consecutive factorials and use that accumulated sum to calculate the sum of any consecutive factorial really quick. Okay? I will skip the details.
Sorry.
Yes.
Can you write with another color? It's hard to see.
Yes, sure. You want me to write this again, or just for next part? Okay, and then the third problem that everyone solved was the one about palindromes, drawing padding substrings.
If you turn the light on, it will be better.
So in this problem, we have some string and we want to count for substrings that are anagrams of some palindrome. Right? So to know if a substring is an anagram of a palindrome, we just need to count that the number of times each character is repeated is even, with the possible exception of just one character. Right? Because if just one character is odd, then we can put that in the middle, and all the others have to be even because they have to be repeated on the right part and on the left part of the palindrome. Right? And the thing is that from the length of the string, we cannot check for every substring, we cannot count manually how many the total amount of each character, because that will lead to an n cube implementation. If we take the string and we try each substring and within the substring we do another iteration to count, then it will be too slow, but it is enough to, when we are considering substrings starting at a given point, as we increase the substring to the right, we can accumulate how much of each character there is. So how many A's, how many B's, how many C's, and so on. And then also maintain a variable of how many odd or how many even. So how many characters with odd total number, or how many characters with even total number. Or we only need one of these because the other one is 26 minus, right? And then each time we see a character, we update the amount, and then we know if it changed from, since we know the total amount, we know if it changed from odd to even or from even to odd. And each time we see that in the odd, the total number of odd amounts, it's 1 or 0, then we count one more substring, and that's it. Okay? Good. 3 problems in 5 minutes. If we keep up like this, we're going to finish in like 15 more minutes or so. Okay. So let's go to the problems that we were at least somehow interesting. I think the next easiest one, easiest in the sense that more people solved, was 2 points revisited. Maybe if I mix the estimated difficulty of 2 is not really a problem. So for this problem, we are given 2 points, x1, y1, and x2, y2. That form a segment. That represents a segment. And we are asked to find a segment that is perpendicular to this one, right? And also we are said, okay, we are said that the city has some boundaries that we don't know, or that can be any number. And the only thing we are sure is that they are bigger. I mean, the city is squared, and the only thing we are sure is that it's bigger than all of these coordinates because all these 2 points are inside the square. Okay, so we have a square that maybe in the worst case maybe like this, right? Maybe bigger, but we don't know, and we have to make sure that our output fits within this square. Okay, so no coordinates. So just to be sure, no coordinates of the output can be above the maximum of these 4 numbers. Okay, and modulars is also 2 points, such that the segment they form, let's put them back, is perpendicular to the input segment. Okay, what does perpendicular mean? Well, there are several ways of defining perpendicular, and the best for this problem is to take the slope. You know what slope is, right? Okay, so the slope of this segment, the input segment, is y1 minus y2 over x1 minus x2, right? And we know that for something to be perpendicular, the slope has to be the opposite and inverse of the input slope. Okay? Okay. So the opposite and so we need minus y1 minus y2 over x1 minus x2. 2 to the minus 1. Okay? This is the expected slope. This only in the case. So this only works when x1 minus x2 is not 0, and this will only work, and this will only work when y1 minus y2 is not 0. Okay, otherwise this is not really well defined. Okay, but since we are not really ultimately going to calculate this, it really doesn't matter. But so let's assume it works, and let's assume that dividing by 0 gives something like infinity or something like this, and then everything will work out. Okay, so then we can, just doing some math here, we can see that this is just x2 minus x1 over y1 minus y2. Okay, just flip the fraction and then flip the sign of one of the two signs, right? And since this looks more or less like this is basically by definition the slope of y1 x2 y2 x1. Right? And then we can check that even in the case that both x coordinates are equal or both y coordinates are equal, this also works. Okay? But this is more or less the proof of why this works. You can also know, I mean, it's not an unknown fact that these are the two vertices that are opposite to these two in some square in the sides. And since we are using the same coordinates, we know that we are not exceeding the maximum possible. Okay? So this is the fast way to solve it. There's some also easy enough, but not so, because this is a one-liner, right? You need to read the input and just output this. Some other way to solve it is to calculate, okay, with some similar analysis, we say, okay, we need this difference for x and this difference for y. So in the output, we will need this difference for x and this difference for y, and just try to make the difference as close to 0 as possible, and then check whether that exceeds the coordinates or not. That way, as I showed here, since there's always a solution, and this solution is optimal in the sense of how little the coordinates are, then we are never going to exceed the maximum available coordinate. Okay? But of course, if the idea came to us like that, and we are not sure, it's faster to just check that we will not exceed the coordinate than to think about why it may never happen. Okay, so even this solution was a little bit longer, but not so difficult and also not so long. So it's likely that some people need this other solution because it's more immediate to think about that than is to do this kind of analysis, unless you knew this fact that flipping coordinates work. Okay. Any comments about this? Or any other idea of the different solution? Okay. Good. So let's change part. So the next one, I'm not sure, was the one with the kangaroo? The fifth that most people solve? So in this problem we are given several cameras and several kangaroos, and we are asked which is, for each kangaroo, which is the camera that sees it better or something like this. Right? So a camera is something, it sees an interval. So we have, let's say this is the real line. So the positive part of the real line. And then a camera sees an interval here that we are given as input, and it sees better things that are closer to the middle. Okay? So actually things here in the left or right end, it doesn't really see all that well. It sees with coverage 0. And then the coverage increases as we get to the middle point, and the middle point is maximum. So the function for a given camera, the function of the coverage it has, is something that looks like this. Right? And this middle point may not be an integral coordinate because if the difference between, these are integral coordinates in the input, but if the difference is odd, then this point is going to be in a non-integral coordinate, but it's not really so. Okay? If you want to make it, if you want to assume it's integral, it's better to just multiply by 2 all the coordinates in the input, which basically gives the same answer. And then this middle point will also fall in integral coordinates. So we have a camera, and we have this as the coverage function, where it's more like 45 degrees, right? And then we have several other cameras. And we are given a whole bunch of these kind of triangles. Okay? And then when the kangaroo appears, so the kangaroo appears in some point, like I don't know, let's say here, here, and we are asked, okay, which is the camera that has the highest coverage? Which translated to this drawing means which is the triangle that has the highest value on this point. If we think of the functions as total functions on the real line, so this is 0 everywhere, and it's valued as this triangle in this range, and this is 0 from here to 0, or from here to infinity, and here is valued as in the triangle, and so on and so forth. We're just asked for a particular x, which of these family of functions has higher value. Okay? And then break ties with some simple rule. Yes? Good. So, to solve this, we can use the thing some trick I mentioned on the first day, which is we can use segment tree because we are calculating maximums. So we can use a segment tree or a binary indexing tree to put all of these linear functions. Right? We can think of this as this is a linear function in this range, and this is a linear function in this range, and this is a linear function in this range, and this is really a set of linear functions. Right? And for particular points, we want which is the linear function that takes the highest value. Okay? So suppose we have the regular range minimum, or in this case range maximum query segment tree on this line, but we add lazy propagation of updates for updates of the form. Calculate the maximum between current value and this linear function. Okay? So we say, okay, insert this linear function in this range, and then we do the insertion as I explained the other day for the lazy propagation. So in each node we keep a mark of what is the linear function that is highest. Okay, so when we have a node, and then this has some pending update, pending, I don't know, some linear function. And then some new update comes with some other linear function. And then since this node represents some range, so what we have to do here is calculate which of these two is larger in which sub-ranges of here. But since the two linear functions, since they are both linear functions, they can intersect in one point. If that point is inside the range, that means that one of them is biggest on one middle of this range, and the other one is like the largest on the other middle. Okay? But they cannot really intersect all that much. Okay? Because they are linear. So what we do is when a new update comes and we have an update pending, we calculate the crossing point, and we calculate which is the largest on the left part and which is the largest on the right part, and then we propagate those two updates to our child. Right? So one of the childs of this node, or not childs, but the thing that covers this range. Right? So we split into two updates that are some range, that are sub-ranges of the range this node is representing. Okay? Sometimes it's going to be that one of the linear functions may be completely below the other, or the crossing point may be outside range, in which case we just need to keep one of the two, the one that is largest. And to test which is largest, once that we know the range where the largest never changes, we just test any point in the range to see which is the best of the two linear functions. Okay? And then really we are not really going to query for ranges. For the maximum we are just going to query, okay, which is the maximum of a given point. But a given point is also a range. It's a range of size 1. Okay? Okay, this is one, like the most straightforward way to implement the problem. So did anyone do anything different? There are some other ways to solve it. Yes, so someone wants to say what did you do?
I did a binary search on the answer to the problem.
Binary search on?
The answer to the problem, the maximum range.
Okay, and then?
Suppose I want to check if D is a possible answer. Then I need to check if there exists a segment such that kangaroo is at least distant D from both the extremes of the interval, right?
Right.
So in order to do that, we sort all the segments from that.
Oh, you do another binary search?
Yes.
On the endpoints of the...
Yes.
Okay. Did you understand? So that's probably easier. So the idea he's saying is, okay, for any point we can do a binary search on what is the maximum achieved, right? And to see if some given value can be achieved, it basically means that it's close enough to some point, right? We can do, so did you put all the points together, or did you have left endpoints and right endpoints at different arrays?
I sort all the left points and then did arrange the maximum query on the right point.
Okay, because you can do binary search on both. One to one side and one to the other side. So you did it more or less. So let me explain the all binary search solution, and then I explain what I think you did. So we want to know in order to binary search, the question we need to answer is given coordinate, given point here, a given value, we want to know whether there's one of these segments that goes above this, right? So we can split the segments into two types, the ones that are increasing and the ones that are decreasing, right? For the ones that are increasing, this means that this point is not too far, it's not more than this amount, it's at least this amount far from some left endpoint, right? So then if we have all the left endpoints sorted, we can binary search for the one that is less than this, like the greatest one that is less than this, and then we can check whether that fulfills the condition or not. Okay? And then for the right endpoint, we can do the same, but in the dual way. Okay, and if we find both, then we know that it's going to work. So what he did, I think it's kind of a mix of both these solutions. So you did a binary search and then arranged minimum query.
I did a binary search to find which segments have the left endpoint before the kangaroo.
Right.
And then I arranged maximum query to check if there exists among these segments
one that goes also on the other side. Okay. Okay, it's like because you compress the segments. So remove from each range, you remove the part that doesn't work. So the part that that is arranged but is less than this, symbolically remove. And then, so then we have collection of intervals, right? Once we remove the part that doesn't work for a fixed height. Okay? And then, for this collection of intervals, he binary searches for the left endpoints to see the ones that are not, to remove the ones that are not good because the left endpoint starts after the point we are looking for, and then amongst the ones that remain, he does a maximum query, right? Because it's right, to find if there's at least one that has the right endpoint on the right side of the point we are querying. Okay? Good. So there's another solution. Okay. Did someone do anything different than these two? Yes.
First of all, I observed that I can remove every interval that's inside another interval because it will never be better.
Right.
So
No. Like if you. Oh right. Yes.
so then if I sort the intervals by the begin, it will be the same. Then if I sort it by the end, then I find the last interval that begins before the point I want to build the coverage for this point.
Also with binary search.
Yes, and then I just have to all the intervals that the begin is closer to the point than the end. I can binary search them to find the leftmost one.
Right.
Then I have to check just two intervals to see which one is the best.
Right. Oh, you do the same for the right side.
No, I don't have to. If I draw it to better
Yeah.
listen. Here's the point. It's not here.
Speak loud.
Okay.
So they can.
Is X the point I want to know the coverage for? Then I have interval that begin here and then here. I have also intervals that I find this interval. That's the last one that begins before the beginning point. So I observe that if this interval, for some interval here, if its begin is closer to the x point than its end, then all intervals from here to here, their begins are closer to the x than the ends, because the order of the interval that begin ends is the same. So I can do another binary search to find the farthest point here that is closer to the x than the end. Okay, the interval that the end is,
Okay.
is closer than.
And then why do you have to check two intervals? That's
Because then I have to find the interval that the end point is closer.
Oh, you have to do exactly the same but reverse.
I don't have to do because it will be first. If this is the leftmost interval that is the beginning is closer to x, then this point will be the
Oh, right.
rightmost.
Okay.
interval.
Okay, so let me recapitulate for everyone. So just in case it wasn't clear. So the idea is first, because these slopes are always 45 degrees, right? So smaller ranges are always, if something is completely contained, it's going to be below or equal to the larger range. Okay? You know, if you have here something contained, it will be like this. Right? So he says, okay, first remove every interval that is inside some other interval. Okay. Then the intervals can only overlap like this. They can also be holes without interval, but they only overlap like this. So with this invariant, the order of the left endpoints of the intervals is the same as the order of the right endpoint of the intervals. So what happens, since this is true, what happens is that of all the intervals that cross a given coordinate, as we move the left endpoint closer to the coordinate, since the order is the same, the right endpoint moves farther away from the coordinate. Okay? That's what means that the order is the same. Then the function distance from left endpoint to coordinate minus distance from right endpoint to coordinate is strictly well, increasing or decreasing depending on which. But in this case, if we move like this, it's going to be strictly decreasing. Okay? Because this amount, this distance is going to be decreasing, and this distance is going to be increasing. Okay? So the distance from left to coordinate subtracted by the distance from right endpoint to coordinate is going to be increasing because it's an decreasing function subtracted an increasing function. Okay? Then we can binary search for the optimal from the point that has closest to 0. Because this difference is 0 exactly when this coordinate is in the middle of the range. Okay? And it's closer to 0 as close as this is to the middle of the range of the camera. Okay? So when we binary search, since unless there's an exactly optimal way, so one that has this function exactly 0, we can find the two that are closest to 0. So the smallest one that is positive and the largest one that is negative. Okay, and then we check those two to see which one of those two is better. Okay? And then in all solutions, we have n log n time for setting up, because in all solution we need to sort the left endpoints. In this case, we have to do insertions in a segment tree, but in all cases it's n times some logarithmic thing, or n log n for sorting, for setting up, and then logarithmic time to solve each query. Because of some binary search, or, well, I guess yours is log square, right? Because you have binary search on the amount, and then the log square for each query is still good enough. Okay? And in this case, it's just a single binary search, so it's logarithmic, and in the solution I explained at the beginning when the necessarily big structure, it's also logarithmic time because we have to access the node, the value on the node. And remember that since we are using lazy propagation in this solution, for accessing the node we cannot really, even if we have the segment tree on an array, we cannot just go to the position of the array and get the value, because we may have some pending updates above, right? We have to always access, when we use lazy propagation, we have to always access the nodes from the root down to the appropriate node to ensure that all pending updates will be split before we access the node. Okay? So even simple access of a single value is going to take logarithmic time. Okay? Any other solution? Okay, then I guess there are also plenty of combinations of these ideas that also should yield the solution. Okay. Any other comment or something about this? Okay, so then all solutions more or less are n log n, or yeah, pseudo-linear in the input. Okay, then let's go to the one that is GCD XOR. But there's, well, I know two ways to solve this. I will explain the easiest one. But both depend on a property which is A XOR B is greater than or equal to A minus B. Okay? And do you already know this property, or do you want me to? I can prove it in like 2 minutes. Okay, I guess not everyone knows it. So the proof is by induction on the number of bits of the, so assuming A and B has the same number of bits, because otherwise the XOR makes no sense. So let's do the proof in the number of bits of both A and B. So if they have 0 bits, if you let me do the easy base case, if they have 0 bits, then everything is empty. So here is 0, here is 0, so it's true. If you don't like the 0 bit thing, if they can only one bit, since this is always positive, the only counterexample could be when A is 1 and B is 0, because otherwise this is not going to be positive. Okay, and this is always non-negative at least. So, and when A is 1 and B is 0, this is 1 and this is 1. Okay, so good, for one bit it works. And then if you have multiple bits, so here we have A XOR B, and here we have A minus B. Right? So to rewrite this, we have some, so we have the first bit of A, the first bit of B, and then we have the rest. XOR, and here we have subtraction. So if the first bit of A and B is equal, then both the XOR and the subtraction are going to basically eliminate the bit. Oh, sorry, and then this is true if A is greater than B. Okay? Otherwise, you have to put absolute value key. Well, I guess it's true because this is negative, it doesn't matter. So if the first bit is the same, then the XOR of this, so let's call this A prime and B prime, A prime and B prime. So the XOR of, so then if the first bit is the same, A XOR B is equal to A prime XOR B prime, and A minus B is equal to A prime minus B prime. Okay? So then by inductive hypothesis, if this is larger or equal than this, then this is larger or equal than this. Okay? Because the prime versions have one less bit than the versions we are analyzing. So if they are different, since A is greater than or equal than B, we know that this is a 1 and this is a 0. Okay? So then, in the XOR, we are going to end up with something like 1, and then here is A prime XOR B prime. Okay? And the subtraction, two things can happen. Right? We can have A prime greater or equal than B prime. Right? This is the easy case because if this is true, then we are going to end up with 1 and A prime minus B prime here. And then again by inductive hypothesis, since this is greater than this, then this whole thing, which is just adding in both sides some power of 2, this is going to be also greater than this. Okay? But the bad case is when B prime is less than, greater than A prime, in which case, in here we are going to have the reverse, right? But if this happens, that means that we are going to have a 0 here, right? Because when we are subtracting, if this is greater than or equal to this, the only way to make the subtraction is at some point to borrow this one for subtracting. Okay? So then we are going to have a 0 here, and if we have a 0 here, it's clear that this is less than this. Because this has a 1 in this position, and even if this is all 1s, it's still less than this. Only this one. Okay? So there is a proof. That's all the cases. Okay. Is this clear? Good. So then we have the property that A XOR B, if A is greater than B, A XOR B is greater or equal than A minus B. Let's leave it there. And then we want to count the cardinal of the set of A's and B's such that 1 is less than B is less or equal than A, less or equal than N, and N, this for some N. Okay, that N we are given in the input, and N can be really big, like 30 million. Okay?
Seven.
Sorry?
7.
7?
10 to the 7.
3 10 to the 7.
3, 10 to the 7.
Oh. Thank you. Okay. And, oh, sorry, yeah, and I'm forgetting something here. Really important. And the GCD of A and B is equal to A, sorry. Okay? So then let's fix some particular element of this set A and B. Okay? So we know that A is greater or equal than B, and we know that the GCD of A and B is equal to A. So from here, from this, we know that this is equal to the GCD of A minus B and B. Okay, and of course, since these two are equal, this is also equal to A. So, and this is less than or equal to A minus B. Okay, because the GCD between two things is less than or equal to both things. Right? So this is less than or equal to A minus B. So then A minus B is greater than, sorry, is greater than, oh no, I'm sorry. Okay, so this is less than A minus B, and then X or B is less than or equal to A minus B, and from the property A X or B is also greater than or equal to A minus B. So therefore, A minus B has to be equal to A X or B. Right? Okay. So then we can add this here without changing it. This is also equal to A minus B. Good. So now we know some powerful thing, which is that the fact that the GCD is equal to A minus B. Okay? So for that, so then we have to check the pairs of A. So we need the pairs of A, B such that their GCD is equal to their subtraction, and those are not that many pairs, so we can check them all. So because let's say D is equal to A minus B, then we want the pairs B and B plus D, okay, such that so the GCD between B and B plus D has to be B, right? No, B. Okay, so that means D has to be co-prime with B. I mean, if D has to divide B, okay, because by definition D divides B and D divides B plus D, and that reduces to just, and this is if and only if D divides B. Okay, and that's true for any. So we can generate all pairs A and B just by checking all possible B's and all possible divisors of B. Okay, and there are not that many pairs of these, even for big N. I mean, by not that many, I mean we have to iterate every B up to N, or almost up to N, and then every divisor. And since the accumulation of the number of divisors is not as big, because it's basically the same as we do when we calculate prime numbers using Eratosthenes. We are basically doing that. We are iterating numbers and their divisors, right? So we know that the number of pairs, the number of these pairs D and B, less than or equal to a given N, is up to N log N. Okay. Now we have to do an additional trick, because since we have a lot of queries, but each time we calculate a pair, so we're going to calculate all possible pairs less than the maximum N, right? And for those pairs, we know that we have to count them for several N's. So we just annotate the smaller N where we have to calculate, where we have to account for this pair, And then after we do this for all pairs, then we accumulate to have the answer for all the queries. Okay? So when I will repeat this because it's kind of complicated to say. So we find the pair, let's just call it AB. Then we know that this is going to be accounted for n equal A, because A is the largest one, right? Yes. For n equal A, for n equal A plus 1, for n equal A plus 2. So for every n greater than or equal to A, we have to count for this given pair. Okay? So we have an array, and at position A, we add 1 for this pair. Okay? We don't add 1 for all these, we just add 1 for here. And when we are done, we accumulate this array. So basically take each position to be the sum of every number after the position that we can do with a single pass. Okay? And then that will be like this plus 1 we have put in every position from there to the end. Okay? So we pre-process every possible n at the beginning and then just answer queries with this array. And to iterate the pairs, and of course, so since we are going to iterate in such a way that this always happens, then the fact that the GCD is equal to the subtraction is going to come as free, right? I mean, if this happens, then the GCD between B and B plus D is going to be equal to D. Okay? Yes.
You already knew since the beginning that D divides B because D is the GCD between A and B, right?
Yes.
So why all this path to?
No, but here I have the if and not if, right? So in general, yes, the difference divides the GCD. So, sorry, the GCD divides the difference if it's positive. But we are not sure that this is enough for. Okay. Okay. So the only thing we need to check is whether it is true that A minus B, so D is equal to the XOR. So we have to iterate the pairs and then check that if D is equal to B plus D XOR. No, sorry, XOR B. Okay? Because this may not happen. Right? So, yeah, so to iterate the pairs, what we can do is, since we know that D divides B, we can just iterate D, and for each D, iterate of possible multiples of D up to n. Right? So we do for D equal 1, D less than or equal to n, or actually it's not n, right? Like max n, because we're going to do every n together. Plus, and then for k equal to, yeah, 2 because 1 never works. K less than max n over D plus, and then here D times. And then here we do the check and we add to the array and everything. So we do this check, and if it's true, we add 1 to the array, and then after this we accumulate the array, and then we answer in constant time every query with the array. Okay? Good, so then these two fours, you can see that they are exactly equal to Eratosthenes' creed for calculating prime numbers. Right? We go to max n and then we iterate something that takes the limit. So we are doing it in a strange way, because in the Eratosthenes we usually start with k equal d, and then do k plus equal d, right? But the number of iterations is basically max n over d. Okay, so this is here we're using the fact that these two iterations only take n log n time, or max n log max n time, and not really max n squared time. Okay, any questions? Did anyone do anything different? Everyone did this? Okay. Well, everyone that solved the problem had the idea for the problem? Okay. Okay, let's do one more. And then take a break. So I think the next one is the game of MJ. Right? Or Fiasco, I'm not sure. Okay, let's do a game of MJ. It's not important that the order is strict. Problem is it's not as difficult, but the statement is kind of hard. So we are given several of these. Of these displays that have L digits and are in base B, so each of the digits each of the numbers contains a digit between 0 and B minus 1. So L and B specify the display. Then we are told for each of them we have a button, they all start at 0, and for each of them there's a button that ups the number by 1. Okay? And we have a couple of these up to 10. And we are told that with some other L1 and B1, L2 and B2, and so on, up to L and B. And then we are told that two players, M and J, are playing a game. In the moves of the game is just pressing a button. Okay? And then the loser is the player that presses a button and makes the addition of all the numbers in the displays, representing as a base B in the corresponding base, is a multiple of 3. Okay, so at the beginning, since everything starts at 0, and also we have no button for the least significant digit of every display. Okay, so at the beginning the summation is 0, so the first player has to press something, and then that will increase the summation. If it increases and is a multiple of 3, then he loses. Otherwise, the second player plays and he has to press a button, and so on and so forth. Okay? So the first easy observation is that all that matters is whether each change, how much the modulo 3 increases with each pressing. Okay? And since pressing, so basically pressing a button means adding to the total summation some corresponding base to some position. Okay, so if I press the shape most least significant digit, the button corresponding to the shape least significant digit in the ith display, then I add to total summation bi to the shape. Okay, because it's the value of the digits in that position. And we also have some limit that says, okay, this button can be pressed only bi times. Okay, so we really only care about these amounts modulo 3, right? Because all that matters is whether the summation is multiple of 3 or of 1 modulo 3 or 2 modulo 3. And then there are really not that many cases. So if bi is a multiple of 3, does everyone is familiar with this notation? Good. So if this is true, then bi to the j is a multiple of 3. If bi is congruent to 1 modulo 3, then bi to the j is also 1 modulo 3. And then if bi is 2, also minus 1, then bi to the j is equal to, it's 2 modulo 3 if and only if j is odd on. This is on, j is on, and bi to the j is 1 modulo 3 if and only if j is here. Okay? And then for each possible j, I mean for each display, for each possible j, we get bi presses of a corresponding button. So we have three kinds of buttons. We have buttons that are modulo 0, buttons that are modulo 1, and buttons that are modulo 2. Okay, so the first thing to do is know how many of them we have. Okay? So to count the modulo 0, we just have to, for the displays that have a base, a base that is a multiple of 3, then we add L. So for each I, such that bi is a multiple of 3, we add bi times L sub I buttons of this congruence voltage. Okay? So we iterate. If for each I means for each possible display, that is a multiple of 3, we add this amount. So we have L buttons, and each button gives us bi presses, and all those presses are valued 0. Okay? So then, for each I that bi is 1 modulo 3, then the same but with 1, right? Because we know that all the digits in that display are going to be worth 1 modulo 3. Okay, so we add bi times li buttons of 1. And then, again, for each I, such that bi is 2 modulo 3. And then we have to do two things. We have to add the ones that are 1 and the ones that are 2. Okay? And then, so if L, so the number of odd j between 1 and L are always L over 2. So both are L over 2, but since we're starting with the odd ones are going to be rounded up, and the even ones are going to be rounded down. Okay? So here we add bi times L sub I over 2 buttons of it is of 1, and then also add bi times L over 2 that rounded up. Okay. Okay? So this we can do really efficiently because there are only a small number of i's, and all the rest is arithmetic. Okay? So then, after we do this, we have the complete specification of the problem in 3 numbers. How many buttons that we have that can be pressed that change 0, how many buttons we have that change 1, and how many buttons we have that change 2. So that increase 2 in modulo 3, the summation of the total. Okay, so then, so now, at a given moment, the player has, initially we can think that the player has 3 choices. He can either press one of the modulo 0, modulo 1, or modulo 2. Okay? But since he cannot get to a position in which the number is a multiple of 3, he only has 2 of these choices. So if the current congruence is 0, then he cannot press 0. If it's 1, he cannot press 2, and if it's 2, he cannot press 1. Okay? So, and also, after the first move, so So we can consider the two possible first moves separately if you want. So after the first move, players can always press 0 because the whole thing is never going to become 0 until the end. So they can always press 0, and then they are, and if they don't press 0, they are forced to press either 1 or 2. Okay. So what does it mean? This means that basically after the first move, pressing 0 is like passing in some way, but there's only a limited number of passes. Okay. So if the number is even, then really nothing happens with the pass, right? Because each player can pass this half the times. So if passing is a good idea, then player 1 passes and player 2 passes again. And the parity of the number of zeros is maintained. Okay? But, so if Newton's of congruence modulus 0 is even, then we can consider it to be 0. Then we will not use it. Okay? Because this is just a simple game theoretic argument. If it's a good idea to pass, then both will pass, and both will pass until all the zeros are used, and then they will keep going with the rest. Okay, so this is kind of the advantage to the second player. Okay? And then, if it's odd, that means there is 1 pass for free. So that means the advantage is to the first player, because he can pass it wherever they want. So if the position without considering the button 0 is losing for the first player, then he can pass and get to a winning position. Right? And if it's winning, I mean this complements the result. Because if the position is winning, then after the first play, the second player passes, and then so if the position without considering the modulo 0 buttons is winning for the first player, since the first player cannot press 0 the first time, he will press something. The second player will get to a losing position, but then the second player can pass, right? And because these are odd, he can pass and pass to the first player, and now the first player is in a losing position with an even number of modulo 0 buttons. Okay? So this means that then complement result. Right? So in any game with force moves, if you give a single button a single pass that any of the two players can use, that basically complements the result. If it's zero sum and it's finite and then some player is going to win. Okay? Because basically pass means, okay, from a losing position I get to a losing position. So that makes any losing position be a winning position and any winning position be a losing position. Okay? Okay. Good. So now all we need to do is calculate what's the result for no modulo 0 buttons. Okay, so we only have two values, the number of modulo 1 buttons and the number of modulo 2 buttons. And moreover, the players are forced to play in an alternating way. Right? So if the first player plays modulo 1, then the second player has to play modulo 2, the first player modulo 1. So each player is always going to press the same button. Okay? So then we have two cases. If the two numbers are different, since every player has to always press the same button or lose, first player press 1, the second leaves at 1, the second player has to press 1. Right? Then 2. So I press 1, let me see if it's correct. So I press 1 and I leave it at 1. Then the second player press 1. So he leaves it at 2, so now I have to play 2. And I leave it at 1. So 1. Okay? But it's a forced. Oh, sorry. I'm mixing up. So let me just say. Okay, so the way the players press the buttons is fixed. Okay? And it's not only fixed, but since there are only a limited number of states, so there are 4 possible states. Either player 1 plays and the current congruence is 1, player 2 plays and the current congruence is 1, player 1 plays and the current congruence is 2, and player 2 plays and the current congruence is 2. Right? All that matters in the state of the game, besides how many buttons are remaining, is who plays, whose turn it is, and what's the current congruence of the summation, either 1 or 2, after the first move. Okay? So then at least there's with this first move, there's a small cycle on how they may play. Okay, so then we can simulate the entire game, since it's deterministic. After we discover the cycle, we can simulate the entire game just by dividing, just by noticing how many presses of each kind of button the cycle takes, and then checking, depending on the amounts of both the number of modulo 1 and modulo 2 buttons, which one is going to run out first. Okay? So you can simulate, but not really by simulating the whole thing, but speeding up the simulation to see who's going to win. Okay? And then if this was the case, then we complement the result. Okay? Okay, so this is more or less also the kind of problem I was telling about, like that is good to train, right? Because there's not really an extremely difficult technique. Even the concepts of arithmetic used or the concepts of game theory used are not really advanced in any way. It's just a matter of patiently putting down all the cases and dividing into cases and considering the possibilities, but no advanced knowledge is needed and no extremely creative idea. Just careful analyzing the cases. The important thing is that since there are many of them, and here I'm not doing the implementation, so there are more details than the one I gave. And it's important that when you do it, you don't get discouraged in the middle and like throw the thing away because it's taking too long or something like this. Right? Okay. Any questions? Any other solution, different idea? Okay. Okay. So let's take like 10 minutes break and come back for the rest of the program.
Precisa completa, assim.
Eu acho que essa opinião, essa
bajándole a todo, en vez de la aplicación de nada y la que vas a hacer como pero ahí la verdad es que no va a aplicar, la verdad Okay, let's continue with the fiasco. I think there was one solution, right? This one. Who solved this during class? Good. You want to tell your... So in this case, because this really has like lots of possible solutions. So what's your idea?
It's basically to do a breadth first search from the source and attribute weights to the edges you used to during the search.
Do a BFS?
Yeah, you do a BFS, and for each edge you visit, in the order you visit, you attribute an increasing weight starting from 1.
And you...
I could prove it's right.
But you prove it during the... You do this beforehand or you prove this during the conference?
No, during the conference.
Okay, yes. So this is the same solution, right? So there's a property, this is not really well known, but is that if you run a BFS on a weighted... So if you basically... Because the algorithm that is given in the statement is basically Dijkstra, but the priorities are wrong. Right? So if things are popped from the priority queue in the correct order, then the algorithm will be correct. Right? Because the invariant of Dijkstra otherwise is maintained. If you process the nodes in the increasing order of distance from the source, then the calculations are exactly as that. Right? But since the priorities are wrong, basically that means that this is not exactly Dijkstra, but it's Dijkstra, but the way we transverse the graph is just any BFS, not necessarily the BFS tree that works for Dijkstra. Okay? And then the solution that he's proposing, which is the same I know, is that this ordering is if we make this ordering or any of the possible orderings correct with respect to the invariant of Dijkstra, then the algorithm will be correct. And if we put the weight on the edges in the order that the breadth first search encounters them, that will make the order of the breadth first search equal to the order of the distances from the root. Okay? So since we are assigning the edges in order, each time we discover a node, we are going to assign a priority that is greater than the priority of the previous node, because we are going to use a new edge and we are using the edges, the weights, in increasing order. Okay? So then we are going to end up taking the nodes in breadth first search order. And in the case that the weights are increasing from the root to the leaves, then in the BFS tree, then that makes the BFS tree be equal to the Dijkstra. Okay? Then with this kind of analysis, there are several other solutions that basically take advantage of this. But this is the easiest one. Okay, but there's plenty of ways. Okay, are there any questions? I don't have really much. I mean, this is really a dot problem. Like, I know, is this property about the BFS and Dijkstra and nothing else? Anyone has a different solution or a different idea that think that may work? Or no? Okay, so then let's move on to the really difficult problems. Okay, let's start with fill the cuboid. Okay. So did anyone try something for this problem during the contest? Yes, what did you try?
I tried backtrack.
Backtrack. What were you getting? What was the problem? Were you into time limit or?
Time limit.
Okay. So what did you do? You just iterated in like from the upper left bottom corner?
Pretty much, but so the 555 cube, the biggest cube we can put is 555.
Yes, that's what I mean is, so you have the, so you started filling at this corner, then try to fill this, if it's not filled, and then try to fill this,
Yeah.
this way of filling?
I tried to fill the 555, and there's just one case that we can fill the 555, that's the case when they give 555, because at the most, the biggest, the cube has
Yes.
125. So, and the 444, you can place at most
Most
one.
one. Yes.
So I pre-processed the place I can put, and then I just do the big backtrack for 3 and 2, because when I finish the backtrack, the place that are not.
Yeah, all the rest you put the one. Okay.
It runs kind of fast, like 0.003 for each test case, but it's too much test case.
Yes, because this can be made even faster. So there are several ways to pass the problem. I will explain two. And then you can, of course, in simple tracking, you can combine a lot of speed ups together. Okay, so first, this I have really no formal argument. It's much better to start, instead of start filling places, so which cube I'm going to put here, which cube I'm going to put here, or nothing. Yeah. It's much better to start putting cubes in size order. So first put all the 3 by 3 by 3 cubes that you want to put, and then put the rest. Right? Instead of putting some 2 by 2 by 2 and some 3 by 3 by 3 alternate. Like the same you did with 5 and 4, also do with 3, because the 3 by 3 by 3 is really big compared to the total size of the cube. So those are going to forbid a lot of combinations. Right? So we're going to truncate the branches much higher in the backtracking tree. If you start with those. Okay, because it's good when you're going to do backtracking, unless it's really obvious for some reason that is going to fit in time. It's good to do some analysis. For instance, so how large can the answer be? Did you find out the maximum answer? Since you have a working solution that. No, well, sorry, the maximum, because you're basically checking how many combinations there exist, right? So do you know which is the maximum number of ways to cover this with cubes? Okay, because the problem here is that since we are processing all of them, it's important that we know that the number is small, right? If it's possible that we have, I don't know, 10 to the 10 or 10 to the 9 possible ways to fill in this, processing all possible ways is not going to work, right? We have to do some way of not processing them all one by one, let's say. Okay? We need to combine them combinatorially in some way. Okay? Do you understand what I'm saying? Because basically, your solution and in general any backtracking solution for this, basically, is even though the answer is just some list of possibilities, what you're doing is basically generating all ways of filling the cube with this, of filling the input thing with the cubes. Okay, and then calculating the answer from this. So it's important that we know that the number is not too big. So there's a pretty bad case here. So suppose you have 4 by 4 by 6, 4 by 7, sorry. Okay? Split this into 4 slices of 2 by 2 by 7. Okay? So here, so each of these, this is the lower bound, right? So each of these we can fill by first choose or basically we can have 3 2 by 2 by 2 cubes and one empty slice. Okay? And each of these we can choose whether to fill it with a 2 by 2 by 2 cube or with 1 by 1 by 1 with 4 1 by 1 by 1 cube. Okay? And this choice we can make independently. Okay? And also we can choose where to put this, for which we have 4 possibilities: here, 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 or here. Okay? Assuming the thing is empty. So that gives, just for one of these, 2 to 3 times 4, so equal to 2 to the 5 possibilities. Okay? And since we have 2 to the 5 for each of these, we have 2 to the 20 ways of filling this, just with cubes of size 2 by 2 by 2 and 1 by 1 by 1, and constrained by this division, which is, so this is not all the possibilities. Okay? But this is the lower bound on the number. So the number is pretty big. So if you're going to consider every possibility, you have to at least do it efficiently. See, on top of that, each time you're in so how are you checking whether you can put the cube or not in a given position? Yes, because you are the only one that said that has some implementation.
I do it by brute force. I search every position and check it.
So you have a 3-dimensional array with booleans and just fill in true or false. Okay, so then checking for the 2 by 2 by 2 cubes also takes some time. Okay, not a lot of time, but you need 8 access to 8 variables, right? And we are pretty close to some bound. And on top of that, we need all the backtracking thing with the filling the Boolean array and remove it when we backtrack. So then we are kind of in a tight position here to process, right? And notice that this bound is even with my previous suggestion of start putting the 3 by 3 by 3 things in the middle, this bound is really hard, right? There's not much we can do about it. Any way we fill the cube, if we process all the possible ways of filling it, we're going to have at least this many leaves in the backtracking tree. Okay? Since these are all leaves, no amount of cutting branches is going to save us from this 1 million thing. Okay, so then this may give us an idea that we have to do one of two things. Either we try to not process every possible combination individually, so to avoid this bad lower bound, or we process everyone because this is still 1 million is possible, but we will do it really fast. Like we try to improve how we do the checkings, like try not to process 8 Boolean variables for the 2 by 2 by 2 cube, which we can do with some bit tricks I'm going to explain. Okay, to process this with just 1 or 2 arithmetic operations. Okay, so for the first approach, and you can combine approaches if you want, but I'm not sure how useful it is. So for the first approach, so try not to process all of them individually. So if we don't do it individually, what can we do? We can try to do something combinatorial, right? Because if we split the whole thing into parts, we can process 2 parts individually and then combine them. Okay, we can do a divide and conquer. If we manage to split them into completely independent parts, right? For instance, if the answer would be counting how many combinations there are, then we split into independent parts, count how many ways are there to fill those parts, and then multiply the result. In this case, it's not a multiplication, but it's still a combination between the vectors of results. So for one part, we have a way to fill it with this many, this many, this many, this many, and the other part, we have some other quantities, and then we combine all the possible sums between a quantity on the left side and a quantity on the right side. Okay? Because both in the case that we only the total or the number of quantities of cubes, the result is much smaller than the number of possibilities. Okay, lots of these possibilities yield the same total number of cubes, right? Because if I choose for this to be filled with 2 by 2 by 2 and this to be filled with, sorry, this is 8 of this, with 8 of these, or the reverse, the total number of cubes I use is the same. Okay, so once I get from the possible ways of filling it to like a summarized result, as long as the summarized result can be combined with some other independent summarized result, I'm improving the running time. Okay, do you see this? In this case, the summarized result is just a fixed array of integers, and it cannot be too big. Right? It's between 1 and 125. So it's a subset of the integers between 1 and 125, and then combining 2 is just in the order of 125 squared, because it's just try every pair. Right? So we have the cube, so we split it somehow. Okay? And then we consider, we get the result from this. So here are the 3, 5, 7, 11, and 13. And here we get 2, 3, 9, and 20. And then we say, okay, we can do it with 2 plus 3, 5 total cubes. We can do it with 3 plus 3, 6 total cubes. We can do it with 9 plus 3, 12, and all the possible sums. And then remove the duplicates. Okay? This is much faster than generating every possibility. Do you see this?
But if you have a cube that takes the middle.
Sorry?
You have a big cube that takes the middle of the...
Oh, of course, of course. So now I'm going to say, okay, so how can we split this? First we need to make 2 independent things. Right? Once we have 2 independent things, we can do this. Okay? So the way to do it is, we get this, and we get the 2 smaller sizes, the 2 smaller sides of the input thing, and then we take a slice here in the middle. Okay? That comprises at most 25 cells. Right? Because the smallest, well, because this is just the cube root square. Right? The smallest, so the largest possible size of the smallest possible side. Okay? And then we first try how we can cover this. Right? But this is much smaller than the entire thing. Once we cover this, we can split between the left and the right. Okay? And then we process the left and right independently, and we combine, and we add whatever many we use to cover this part. And this is for each covering of the middle. Okay, this leads to a much more complicated implementation, but it's going to run much faster. In the worst case, it's going to be the same. Also, because for covering this, we can force it not to use all 1 by 1 by 1 cubes. Right? Because if we use all 1 by 1 by 1 cube, we can just cut directly in the middle and okay? But it really doesn't, it's not really important. But this we cover really fast. Okay, because yes, if it's the 5 by 5 by 5, it's only one possibility, and then we will only have like, where will we put the 2 by 2 and 3 by 3, and there are not that many possibilities. Okay? So that's one possible speed up. And the other possible speed up is to speed up how we manage to maintain the state. So of the cubes we already put, which parts of the thing are already covered and which are not covered, and does this cube fits into, assuming it has the upper left bottom corner in this position. Okay, this is what we want, this 3-dimensional array of booleans. We want to take this into something more easier to update. Okay? So let's start with 1 dimension. So suppose you have 1 dimension, which in this case can be the last dimension of this 3-dimensional thing. So how can we make? So what we need in the one dimension is to update continuous. So we have some values: true, false, false, true, false. And the two operation we need is check this continuous part and tell me whether they are all true or all false, depending on whether true represents empty or if true represents use, so false represents empty. I want to know, I don't know, for the 2 by 2 by 2, or for the 2 in one dimension, I want to know whether 2 consecutive values are false, right? So with using a bit vector instead of a vector of booleans, I can do that with a single check, right? If I want to know that if from position I through position j are all false, this is just a matter of generating this a bit vector with all ones here and zeros otherwise, right? And checking that the and of both of the integer representing this and the integer representing the mask, and the mask is always is ones between the position I and position j. And since the number of ones is limited in the problem, we can have pre-generated the mask. So we can have a mask for length 1, a mask for length 2, mask for length 3, 4 and 5, which is the only ones that we care about. We have all of these pre-generated at the beginning, and then we move them j positions to the right with a single shift, and that gives us the mask. And then we take the and between our mask and the representation of the current state, and that tells us whether they are false or not. If that's 0, then all the positions covered by the mask are 0. Okay? And then when we want to set something, it's just doing OR with the same mask. Right? So we'll set all of them to 1. Okay, so if we do it in one dimension, we at least remove one of the iterations that we need to update this. Okay, so for the 3 and 2, we remove a little bit. But we can improve further. So we suppose we have 2 dimensions. Okay, so we have a matrix of Boolean things. False, true, false, false, true, false. And in this case, the query and the update is done by submatrix. Square submatrix. Okay, so let me know whether this square is all false to see if I can fit something there, and also put all the ones in this square because I just placed the cube there. Okay, these are the 2 operations we need. So we can do more or less the same, but by putting all of these in a single bit vector. Right, we put the bit vector that has the first row, then the second row, then the third row, and then what happens? So suppose we do that, right? We have a bit vector that is stored in an integer variable, and so suppose we want this square matrix, right? This is going to be a mask that takes these two bits and the first 2 bits of the second part. Okay, so this, and then for 3 by 3, it's going to be the first 3 here, the first 3 here, and the first 3 here. So all these we're going to pre-generate because there are 5 of them, right? For the 1 by 1 by 1, 2 by 2 by 2, 3 by 3 by 3, 4 by 4 by 4, and 5 by 5 by 5. Okay, so we pre-generate. And then, as we did here we shifted the mask depending on where we want the continuous part to end. But here we can shift the mask twice. If we shift by simple addition, we move to the right or the left, or depending how we represent. Okay, so if we want this square. Let me check first. If we want to know what happens with this square, well, this square is just this square but shifted 1 position. Okay? If we are moving right, we just shift positions, and then these 2 moves to these 2, and these 2 moves to these 2. Right? So we have a mask that represents the 2 red circles, these 2 red circles. Shifting the mask 1 position represents these 2 green circles. Right? That in turn represent this submatrix. Okay, and if we want to move back, if we want to move to the bottom, okay, we want to move down, then we have to shift by, okay, however many positions this has in total. Okay, if we want this red circle to move, well, here, and this red circle to move here, then we have to shift by this amount. Okay, but this is a fixed amount. It's one of the sides of the cube. Okay, so if we want to move I positions, that way, and j positions that way, we have to shift the mask, shift the pre-generated mask by I plus j times side positions. Okay, that moves the window where we want it. And then with this mask, we do the same as we did in one dimension. We use it to query and we use it to update. Okay? Then we can process 2 dimensions with just one operation. Okay? So then we remove 2. And if we remove the 3rd dimension, we can basically do the same. We pre-process the matrix, so we pre-generate all the masks that represent the upper, so this is harder to draw, but we want the mask that represents this, the mask that represents something of like 2 by 2, always to the corner, and then moving to one side is going to be just the direct addition, moving down is going to be addition times the length of some side, and moving in the 3rd direction is going to be addition times side 1 times side 2. Right? Because this is the regular mapping of things in a matrix into a linear array. Okay? So if we add this, we are basically moving any submatrix around. Okay? So with this way, all the checking in the Boolean vector can be done with it's a couple of arithmetic operations, but these are all arithmetic, right? And only one access into the array. The only problem for this particular problem, the only things that we need to be careful about is that if we try to put all 3 dimensions, I explained it because this works, and this works for more dimensions as well, right? And this works for anything. But in this case, since this can have 125 positions, if we want to do all 3 dimensions, then we need more than 64 bits. So we need a little bit more arithmetic to split the bit vector into 2 parts, right? Into 2 64-bit integrals. So since this is going to add more overhead, I think the easiest way for this problem would be to just keep 1 dimension as an array and make an array of 2-dimension matrices of bits. And these matrices are going to fit in just even 32-bit integer. So each of these matrices you manage with just a couple of arithmetic operations and a shift. Okay? Because do you understand that, right? If we want a 3-dimensional matrix of more than 64 places, we need to simulate that we have a 125-bit integer, and we do not. Okay, so all the shifts we have to take care of whether the shift goes from one register to the other register that represents the number, and that adds a lot of overhead. So that may not really improve the execution time. But changing from 3-dimensional array to 1-dimensional array with bit matrices really improves the running time.
You can store a bit set in a 4-dimensional array that stores the 3 coordinates and the size of the square. So you can process all the possible bit sets, and you just consult the 4-dimensional array.
And why the 4-dimension?
The starting position and the side of the square.
Sorry, I'm not following.
So you use a bit set, 125 bits,
Yes.
to store the mask. And of course, I think C++ we use 2 components for that. And for every possible starting position and side of the...
Oh, you want to preprocess all the masks at the beginning?
Yeah.
Yeah, I guess that will work. Yes. I'm not sure how fast it will be to test the bit set with
It's
the...
simpler because you don't have to think about all this arithmetic shifting, everything.
But what I mean is that the standard library set doesn't give you a way to do bit operations with more than 64 values.
Bit set does that.
Oh, you don't have AND with all the bit set, maybe. Yeah, that may work. Yes, because the generating is not really does not take a long time.
I think it's
Because you generate each position independently, right? Not.
yeah. For every position, we use the mask.
Yeah, that sounds good. Yeah, that may even be faster than what I was saying. But what I really wanted to tell, I mean, for other problems also is this trick of how to put matrices into. In this case, you can pre-generate every mask, so it really doesn't matter how. If you do this trick of pre-generating masks, it really any way of projecting the matrix into the bit vector is fine if you are going to pre-process the mask. But if you put the vector into the matrix in this ordered way, then you can even manage to do this by arithmetic instead of this pre-processing. I know if you have multiple, more sizes of things that can be needed to test. Okay, but that's a nice idea. Okay. Okay, any other comment?
Yeah, there is also something you can do that I talked about after the process. Is that you can like do a point change to see all the possible results you can get. And like let's say you can call the backtrack is saying I want this backtrack to find a solution that uses 2 3x3 3x3 and 5 2x2x2. And if it finds a solution, it never has to.
Okay, so you fix that at the beginning, so you can stop when you find one.
Yeah, when I find a solution, I don't have to do any backtrack that has this type of
right.
result.
And that gives you really.
No, I thought about after the process, so I didn't try it.
Okay.
But
Yeah, I mean that would be good for like this worst case I explained. This one would just really be. You will really improve these cases because all use kind of the same subset. Or lots of the same subsets of cubes. But in general, I don't know how it will work. Maybe it will be really good. I don't know. But yeah, it's a nice way of learning. So any other comment or idea or solution? Okay. So as far as I understand by this explanation I found about these problems, I will send it to you. I think what they were expecting was just this speed up for and try first the bigger cubes instead of trying first the upper left corner because they cut more. But apparently with those two speed ups it was enough to get the problem in the contest. Okay. So let's do now Game of Thrones. Okay, this problem, we are doing a graph. We have the nodes split into two sets, A and B. And we are asked to find the subgraph, so a subset of the edges, such that in the subgraph, all the nodes in one of the sets in the set B have even degree, and all the nodes in the set A have odd degree. Okay? Graph. And we are said, okay, this is A. And this is B. And then find some subgraphs such that nodes in A have odd degree and nodes in B have even degree. And such that the weight, we have some weights for the edges, and such that the weight of the subgraph is minimum. Okay? So the condition of the subgraph, so here we have like, for this example, we have a nicer example in the set. We can have like this subgraph, for instance. But I don't know, if this weight is really big, I don't know, here we have like 1000 and the rest are 1. This will have weight 1001 in total. And there's another possibility like this. Sorry. Here the remain isolated. We have this, and this has weight. Okay, so this one, even though it has more edges, is better. Okay? Okay, so this condition of about the odd degree and the even degree in the result is kind of similar to the condition for Eulerian graphs. I mean, in Eulerian graphs we ask for the graph to be connected and to have all vertices of even degree. Okay? And that's because since we want an Eulerian cycle, everyone know what an Eulerian cycle is? Cycle that goes through all the edges exactly once. Okay. For an Eulerian cycle to exist, we need to be able to enter, each time we enter a node, we need to be able to leave. Right? That's why we need all even degrees. If we want an Eulerian path to exist, we can afford up to two odd degree vertices, because since we need a path, the starting point and the ending point of the path may have odd degree, because the starting point we may leave and never before entering, we may just leave the first time, and each subsequent time we have to enter and leave. And the end point, we can just enter at the end and not leave again, right? And that may make them odd, right? And as you know, the number of odd degree vertices cannot be odd. Okay, since the sum of all the degrees is even because it's 2 times the number of edges, the number of odd degree vertices cannot be odd. So in this case, if the size of the set A is odd, then there's no solution, right? Because no graph will have an odd number of vertices with odd degree. Okay? Good. So let's assume further than that the size of A is even. Okay, so that there's possible solution. Okay, then, so with the Eulerian cycle we have just one cycle. With an Eulerian path we have 2 vertices, up to 2 vertices of odd degree, and we know that there's a single path that goes through it. When in this case, since all the vertices in V have even degree, we can just find paths. We can find the path from one vertex in A to another vertex in A greedily, because we leave, right? Then if we enter a node in B, we know that we have an unused edge that we can leave because of the degrees even. And if we re-enter, we always have, because this is the same as the Eulerian thing. Each time we get to a node, we have a way to leave that we didn't use. And this removes 2. Since the degree is even, every time we get to a node in B, we have some unused edge that we can leave. Okay? So if we start walking from a vertex in A, we're going to end up in another vertex in A. Right? Because these are the odd degrees vertices. And this is true for any node. So basically that means that we can split the whole graph into a disjoint collection of paths. And each path is between a different pair of vertices in A. Okay? Actually, we can have that just with the odd degree and even degree condition. We can have that plus some cycles, right? We could have, I know, here are some vertices in B, and these have all even degree. But of course, since we have minimum weight, any cycle we have in this solution we can remove. Okay? If we have a cycle concerning any node, we can remove, because that removes an even number of edges for each node, so it maintains the parity of the degrees, and of course it decreases the weight. Right? So we can assume that the solution will have no cycles. An optimal solution will have no cycles. Since this is an acyclic graph, then it can be split into the disjoint number of paths between 2 different elements of A. Okay? And for the same reason, all vertices in A have actually, in an optimal solution, we have actually degree 1. Because if one has degree more than 1, doing this greedy path finding, we are going to find a cycle that goes through the vertex. Okay? So all the vertices in A have degree 1, and then it's easy to see that this can be split into disjoint paths between vertices in A. It's important to see that vertices in B can have more than 2 degree, right? Because we can have something like this. This is perfectly valid, right? So vertices in B do not necessarily have only 2, because more than 2 that does not imply a cycle in a vertex in B. But in a vertex in A, more than 1 implies a cycle. Okay, because the paths are between members of A. Okay. But in this case, you can remove some edges. No, sorry. I lied. This was not necessary and I thought it was true, but so in this case, for instance, this has degree 3 and there's no center. And this in A. Okay, but still, I mean, we can split the thing into disjoint paths between members of A, disjoint in edges, not in nodes, right? I mean, in this example, you can see that the nodes can be shared between several paths, but the edges, so this is one path, this is another path, and this is another path. Okay? So let's try to find, so then we can think of the problem as finding a set of paths between members of A such that they are disjoint and they have minimum weight. Okay? Since each solution contains one of these, if we find the minimum of this, and this minimum implies a solution also, so this is not necessarily an if and only if solution, but it's easy to see that this is an if and only if condition, right? If we find a disjoint set of paths between members of A, then taking exactly those edges as the solution yields a solution. Since it's a disjoint number of paths, it will have odd degree for the A's and even degree for the B's, and then it will have minimum weight because we asked for minimum weight. Okay? Good. So a subset of the disjoint paths between members. Okay, so then a way to find this is, let's find all the length of all the paths between all members of A. Okay? Since we can at most n less than or equal to 100, we can just do minimum path between each pair of nodes. Okay? And we will have the length of the path between any two members of A. Okay? And now we want from that, and now we can think about the complete graph of all the nodes in A. This is complete and contains the length between any two of them. Well, if it's possible to, it may not be complete, but maybe up to complete, and we put the length, or we put infinity or something if there is no path. Okay? Or we can just not put the edge depending on the implementation. So then what we can do is find the minimum matching here. Okay? I mean a perfect matching with minimum weight, which is just the maximum matching if we reverse the weight, we complement the weight. And if we do that, we found a number of paths in here with minimum weight, right? But the problem is that we have to prove that they are disjoint. Okay, but the thing is that the optimal solution will always be disjoint because suppose we are trying to choose something suppose we are trying to choose two paths that overlap. Then we can just like read the paths and remove this part and obtain better thing. Right? Obtain two also match these members with smaller weight. Okay, because we remove some edges. We remove all the overlap parts of both paths. So the minimum matching induces a collection of disjoint paths of minimum weight. Because any collection of disjoint paths induces a minimum matching. Okay? So matchings in general may induce collections of paths that are not disjoint. But the minimum matching induces a collection of paths that is disjoint. And the minimum set of disjoint paths of minimum weight induces a perfect matching of minimum weight. Okay? So then the solution, the perfect matching with minimum weight on this graph is exactly the solution. Okay? And then there's a horrible algorithm that no one is actually going to code in code, but there's an algorithm that finds the perfect matching with minimum weight, or actually there's an algorithm that finds the matching with maximum weight, but since it's always going to be perfect, we can just complement the weight and find the maximum weight instead of the minimum and then do something. Okay? Yes?
On a matching, every vertex appears only once, right?
Yes?
But they can appear twice. So
oh, okay. But this is So in this graph, each edge represents a path between two nodes in A. So if the minimum path between two nodes passes through some nodes in B or some nodes in A, this edge is actually representing all the path. So for instance, in this case, right, let's put numbers. 1, 4, 5, 5, 6. You can see the green? Right? So then this graph is going to be, okay, 1 is going to be linked, so if these are actually minimum, 1 is going to be linked to 2 because of this path, it's going to be linked to 3 because of this path. Okay, so this is a different graph. It's the graph of the paths, not the graph of the edges. The graph of the minimum path. Okay? So that's why the matching only contains each node now. So here, if we choose these two nodes, that doesn't mean that this edge does not translate to a single edge of the initial graph. It translates to a path in the initial graph, and it's possible that the intermediate nodes of this edge and this edge are not disjoint. Okay? So this solution, the matching in this solution will be 1 matched with 3, 2 matched with 5, and 4 matched with 6. Okay? But if this edge on the paths graph, on the transformative graph, actually represents the path 4, 5, 6. Because apparently this was the minimum path between 4 and 6. Okay? And this edge represents the path that goes through this node in B, and this edge also represents the path between 2 and 5. Okay? So each edge in this graph, in the graph where we run the matching, represents a path, the minimum path, or one minimum path between the two nodes that is linking. Okay? In the original graph. Okay. Any other questions? So really, you see, there's a lot of different applications of graph theory in this problem, and a horrible algorithm. So in the actual contest, they used the limit for the number of nodes in A much lower than the one that is online. The number of nodes in A was limited by 21, so actually 20 because odd number is never used. I mean, odd number never has solution. So, and then if we have a small number of nodes in A, we can find we can finish this by doing maximum matching with the dynamic programming the subset bitmask.
Still, a vertex can appear 3 times on 3 different matches. Because suppose you have 1 and 3 childs, and the three childs are disconnected. Only connects to the parent.
So you have 1
and 3 childs. And
this graph.
Yeah.
This is the input graph.
Yeah.
And which are the members in A? Everyone is in A.
Yeah. The best choice is.
Yeah, it's everything.
Yeah, but the parent appears 3 times.
Yes, so we have this graph as input. Let's put the weights because really the weights don't matter, right? So
It's
suppose,
not a mesh.
but from this graph, we are going to build the graph of the minimum paths. So let's put 1, 2, 3, 4. Okay. So the minimum path between 1 and 2 is 1. It has weight 1. Okay. The minimum path between. Sorry. So let me show you. We don't confuse the numbers. Let me stop filling the A, so I can put the ID inside. We have node 1, node 2, node 3, and node 4. Okay, and all weights are 1. Okay, so when we do the minimum paths graph, we're going to have 1, 2, 3, and 4. And so the minimum path between 4 and any of the others is 1, because it only requires a single edge. And then the minimum path between any 2 of the others is of length 2. Okay, so we have 2 here, 2 here, and then 2 here. Okay, and this is the graph in which we find the maximum matching, the minimum matching, or the maximum matching. Okay, and the minimum matching here, of course, is taking one of these of length 1, and one of these of length 2, or one of these 3. Okay. Okay, only the pair that uses 4 is going to be using an edge of length 1 for the matching. Okay? So the maximum matching is 1 plus 2 equal 3, which is exactly the sum of this. Because suppose we choose as a matching of minimum size, we choose 4, 2 with length 1 and 3, 1 with length 2. Okay? This represents the path directly from 4 to 2, but this represents the path that goes from 3 to 1 passing through 4. Okay? So you don't run the matching in the original graph, in the input graph. You run the matching in this graph. Okay? In which each edge or each pair in the matching does not a single edge of the original graph, but the path in the original graph, and this path may pass through several nodes. Okay? Right. Any other question or comment? Okay, so I mean, this is pretty theoretical, and I think the solution is nice up to the point that we need the maximum matching algorithm. But as I said in the contest, for this part they gave a smaller bound for the size of A, so you can solve this with a simple dynamic programming with subsets solution instead of actually the maximum matching solution. But still nobody solved it during the contest, even with this simplified finish. Because the idea in general is, I like it, but it's complicated. It has a lot of graph theoretic implications. Okay, are there any questions or comments or anything? Okay, so let's move to the impossible problem. Okay, so the problem, the pair chains problem. So, apparently, for this problem, there exists some closed form equation that solves the problem. It's like, apparently it's a sequence not as known as Stirling numbers or Euler numbers, but you can find it in the online encyclopedia of integer sequences or something. But of course nobody knew this other than the problem setter, and I also don't know this, so I don't know the solution. And the suggested solution I found was just knowing that this closed form equation. But what I would like to tell a little bit is some ideas I have that I think may eventually lead to a solution of the problem, but I don't have a full solution, but I think the ideas may be nice for other problems of this sort, so I will tell you anyway. So first we need some arithmetic expression that represents the solution. Okay? So we're said that we have T1, T2, and T3 be the number of pairs of each type. Okay, in a particular arrangement, and then if these are the numbers, the number of possible chains that we can make is T1 plus T2 plus T3 factorial over T1 factorial, T2 factorial, T3 factorial. This is the way to mix them. Since they are all different colors, this is the numbers of ways we can mix them into a single array of T1 plus T2 plus T3 things, times the number of choices we have for the color of each type. So for type 1 we have X, so it's X to the T1 times Y to the T2 times Z to the T3. So now after we fix the type of each jewel, we have to choose the color for each one, and that this is independent choice, so we just multiply. Okay? So this is if we have fixed the number of things of type 1, 2, and 3. Right? So we know that T1 plus T2 is equal to A, given A, and T1 plus T3 this is T1 plus T3, this is T2 plus T3 equal to, okay? So we can replace T1 by A minus T3 and T2 by B minus T3, and this whole thing by A plus B minus B. Okay? Using this. And then, oh sorry, this also. A minus T3. So then the entire expression depends only on some constant and the value of T3. And the possible values of 43 are from 0 to the minimum of A and B. Okay? So this modulo, let's MC prime. So this modulo M is the solution of the problem. Okay? So of course we cannot, since the numbers can be extremely big, we cannot actually calculate the summation by adding up all its terms, because we have a ridiculously large number of terms. The arithmetic part, the arithmetic here is not such a big problem because we run all the arithmetic modulo M. Okay? So the arithmetic is not really a problem with overflow. The only problem is that we have a ridiculously large number of terms. Right? Because calculating a factorial modulo M is, I mean, the difference of the factorials is not that different. So this is the idea. So for this part, so what happens with the factorials? Since this is a prime, all the divisions that are not of factors of M, we can turn into multiplications by multiplying by the inverse, by the multiplicative inverse of the number. Okay? So my idea is to write this as, we have some fraction, so here we have M to the something, K1 over M to the K2, that represent for each possible value of T3, how many times M, how many factors of M there are in the factorial on top, and how many factors of M are between all the factorials in the bottom. Okay, so we factorize everything that is with M. And we know that on top we have to have more than on the bottom because this has to be an integer. This has to be an integer amount. Okay, because it's some combinatorial result. Okay, so we have to have more, the same or more terms M on top than on the bottom. And then we have the rest of the factorial. But this is not really a fraction. Okay? I mean, this fraction, since we are calculating modulo M, we can turn into something that is just multiplying by just for each possible modulo here, take the multiplicative inverse. Okay? Do you understand? The only things that we cannot take modulo M on the bottom, I mean, we can take everything modulo M, but the things that are multiple of M. Because if we take something that is a multiple of M modulo M on the bottom part of the fraction, we are dividing by 0. Right? But all the others we can take modulo M. Right? And that's good because M is big but not so big. Right? So if we have something like, I don't know, M squared plus 1 factorial, okay? This is actually N minus 1 factorial to the N. Okay, this is just, so we are multiplying 1 times 2 times 3 times N plus 1 times 2n times 2n plus 1. But the modulo M part of all these parts is the same. Right? If we discard the M's, the multiples of M, the modulo M of all these parts is the same. Okay? So M plus 1 is 1 modulo M, M plus 2 is 2 modulo M. So each of these M minus 1 factorial, we can just multiply them, and we can do this all of this with exponentiation modulo M. Okay, and then we can count how many M's we have by, so inside N factorial, the number of M factors that there are N over M plus N over M squared plus N over M cubed. Okay? This is clear why this works. And in this case, since M cubed is greater than the maximum possible value already, then it's only this. We only care about this number of factors of M. Okay? So we can do this for the regular factorial, so we can do this for these two. So we take the cases, so we check when, we can check when the number of M's here is greater than the number of M's on the bottom, and all of those are going to be 0 modulo M, all of those terms. So then those we remove, or we symbolically remove. And then for the others, there's some cyclic thing going on. Because when you get from the value of a term to a value of a term, so the value of a term with a given T3 to a value of a term with a given with T3 plus 1, okay, we are just multiplying by a number here, multiplying by a number here, dividing, okay? And as long as we are not exactly crossing a multiple of m, okay, all these divisions can be turned into multiplication. So there's a cyclic thing going on between chunks of length n. Okay? So between T3 and T3 plus 1, the same thing happens as between T3 plus m and T3 plus m plus 1. The same kind of modification. So I think it can be, this cyclic thing can be used to reduce this whole summation into just summing chunks of size m. Okay? But I think this needs really a lot more of math development that I didn't have time to do. But so this was an idea. But this works for several problems, right? When you have a long summation, sometimes it's as easy as applying some identities to sum up a linear, an arithmetic progression or a geometrical progression or something like this. But also sometimes you can find some cycle when you are doing the summation module or something. If you find the cycle on the terms, then you can reduce the summation to just sum some number of terms proportional to the module, if the module is prime. Okay, like if you find, like the same trick is if you want to calculate Fibonacci modulo m, then from the way Fibonacci works, at some point you have, say, since Fibonacci only depends on the last two elements, if you can just, the Fibonacci modulo m only depends on the modulo m of the last two elements. So there's only m squared possible combinations. So at some point you start to cycle between Fibonacci and you can calculate Fibonacci really fast. There's also another way to calculate Fibonacci really fast, but do you see what I'm saying? Okay, so these kind of cycles when calculating things modulo m are really, can be useful in a broad set of problems. Okay, did anyone have another idea or some? Okay, well I will send you I will send to the list of the summer camp these slides that I found that have some summary of possible solutions. So maybe if you don't remember and you don't want to go to the whole video or something, you can check to try to implement them by yourselves, the problems that you didn't get during the contest. Okay, so this afternoon after lunch we are going to have another contest. This is going to be different. It's going to be just difficult problems because this was a regular contest, so we have some easy problems. Now we're going to have just medium difficult or difficult problems taken from two regionals. And well, so let's try to, hopefully the live archive won't mess up again. I checked the problems yesterday, and it is possible to get both wrong answer and accepted in every problem. I'm not sure if they are correct, but at least it's possible to get both. So that seems to be okay. So also, if you run into a problem during the contest like yesterday, and I'm not there right outside, or in the labs nearby, because I'm come to do something else, just write an email to the list, and I will get it, and I will either come or try to find some solution. If during the contest, I know, live archive falls down or something like this. Okay?
Da hora.